Terrestrial magnetism. What is a terrestrial magnetism? Terrestrial magnetism exactly explains the magnetic field of the Earth. Okay. First, before entering into terrestrial magnetism, we supposed to know few terms, which makes us to know how the terrestrial magnetism is existing. Okay. So, first of all, how terrestrial magnetism is existing naturally. How we can say that Earth is a natural magnet? There are so many studies. Earth is said to be a natural magnet. First, initially in olden days, in the 1600 century, there were some scientists. They were adapted. They thought that inside the globe of the Earth, or inside the Earth, there is a permanent magnet, or magnetic materials are existing. Due to the existence of the magnetic material, it is acting as a permanent magnet. But there was a question arised. At the core part of the earth, so much hotness is existing, right? Since temperature increases, permanent magnet existence is questionable. Okay, questionable in the sense we know that if the temperature increases or if you heat a normal magnet, permanent magnet, obviously it turns into a non-magnetic material. I mean, sorry, it turns into a just a magnetic material, non-magnet it became. So this has happened because of the temperature. So since the core part of the earth, the hotness is more, how can we say that that is a permanent magnet is existing because of the material? Then later on, the another study has come into the picture, that is Earth. Earth rotates around itself as well as around the sun, revolve around the sun. This is we know, right? Now, the magnetic field of the earth, how it is possessed, actually basically how the magnetism has existed, from where this magnetic field produced, in the sense only one thing I said previously also, depends on the charge particle. Okay, nothing but who is the charge particle? Electron. If electron is in the motion inside the nucleus, around the nucleus, inside the atom, it revolves, and at the same time it rotates. While it is revolving and rotating in the atom, it possesses some orbital momentum vector. What type of orbital momentum? Spin angular momentum. By its own itself it is rotating, and at the same time by rotating around the nucleus, orbital angular momentum. By these, it also possesses the magnetic momentum, right? So with respect to that magnetic momentum, we can say that particular substance possesses the magnetic properties or not. Okay, this is the exact origin of the magnetic field of study. Origin, from where the magnetic properties generates. Okay, okay. This we keep aside. Now the second point is that since Earth is rotating inside the Earth, there is a circular currents are producing. Due to these circular currents, we know that where there is a current perpendicularly, magnetic field also produces. So perpendicular to these circular currents, magnetic field has produced. This is one study. After this study, next, there are some radiations which comes from the universe, such type of radiation, background radiation, we say some areas it is, we say natural radiation comes from the universe is called as cosmic radiation. This cosmic radiation, what it will do usually? Of course, there is a cosmic radiation. Due to this cosmic radiation, there are the gases. Whenever it is enter into the atmosphere, it ionizes the gases. Due to ionization of the gases, what happens? Whatever the Earth is rotating with around the around itself and revolving around the sun, around the earth, whenever it is entering into the atmosphere, around the earth, whatever the atmosphere is there, total atmosphere, across the atmosphere of the earth, electric current generates. Due to that, magnetic field produces. because of cosmic radiation. This is one way study. Like this, so many scientists are having different hypotheses on this, and few scientists has found inside the core part of the earth there are some liquids, molten wax type of liquids are available, metallic liquids. Due to these liquids, there is large amount of heat energy is generated. Due to this heat, the currents are produced. Due to production of these currents, magnetic field is possessing. This is the way present hypothetical situation is going on with some basic data or basic information. Okay, so this liquid region inside the core part of the earth, which gives us, due to the molten wax, we cannot say wax, molten core part, whatever the metallic liquids are available, due to the metallic liquids, magnetism is producing. This is present scenario or present study is going on. I'm not telling they have denied it. They are also having considered, but presently this is the way the study is going on the terrestrial magnetism. Finally, that all cases, finally they are all possessing the magnetic properties. Who the Earth is producing the magnetic properties or possessing magnetic properties, but it is not exactly geographic south or geographic north, little in different direction to the geographic south and geographic north. Now, if you enter into the topic little more, to understand structurally this terrestrial magnetism, first we need to know some important terms. What are those important terms which we need to know? Geographic axis. What is this geographic axis? The axial line or a straight line which is passing through the geographic poles of the earth is called a geographic axis. Okay? What is this?
Geographic axis.
Geographic axis. If you prefer to take it's a globe in a sense, if geographic north, south, if I prefer. So along this, whatever the imaginary line if you draw, that we take as geographic axis. Around this axis, there is a rotation takes place. Of course, Earth rotates like this around itself. We can call it as polar axis also. Means you can see here like this, the rotation that. Geographic meridian. What is this geographic meridian? Meridian at any place in vertical plane passing to the geographic north and south poles. Let us say, you can see here in the diagram, if this is the earth in the sense, this is the north south in the sense, this vertical plane, whatever we are considering, this part of this vertical plane, we call it as geographic meridian. Geographic equator. Equator, we know it's a great circle of the earth. Whatever I have drawn in the first diagram itself, you know, you can understand the geographic equator is like this. This is a geographic equator, whereas this is geographic axis, and this is geographic meridian, right? Now, which is perpendicular to the meridian is called as geographic axis. Now coming to the magnetic axis. Obviously magnetic axis little tilted with some 11 degrees. Some books has given 11 degrees and some books has given 17 degrees. It's approximately with respect to the axis of the geographic. This is magnetic poles, magnetic north, magnetic south, we can write. Okay, it's twisting. Tilting with respect to geographic axis is how much? 17 degrees. How much it is tilting? 17 degrees. Now, in the same way, how we are having the axis along the poles of the magnet of the earth. So that is called as magnetic axis. Perpendicular to the magnetic axis, whatever the line if we draw. For example, already we have drawn the, this is what? Equator, right? Equator of whom? Earth. Since you have drawn the equator of the earth like this, I will have one more circle which is perpendicular to the magnetic axis. Okay. So whenever it is coming to the magnetic axis and geographic axis which are perpendicular to each other, means which is tilting. Geographic axis also tilting with some angle. Okay, 17 degrees and all. Right? So this we call it as axis nearly at an angle of 17 degrees here it is given, which is inclined with the geographic axis. Magnetic meridian. The same magnetic meridian is quite tilted with the 17 degrees angle with respect to the earth meridian, means geographic meridian we can say. What we can say with respect to the geographic meridian means along the axis of geographic north and geographic south, magnetic south, we are having that meridian is called as magnetic meridian. This is with respect to the geographic south and geographic north magnetic meridian. Okay, so now, in the same manner, you can see magnetic equator. Magnetic equator, already just now I told you, magnetic equator which is makes 17 degrees angle with respect to the earth equator. So I can draw here also. This we can draw as like this, which is perpendicular to the magnetic axis. Okay. When you clear about these things, then the rest of the things will be easy for us to understand. Magnetic meridian is a plane, or geographic meridian is a plane which is in the vertical direction, means along the north south direction of geographic, as well as coming to the magnetic equator along the magnetic north south poles of the equator, sorry, uh, axis. But equator is quite perpendicular to the axis in the case of geographic as well as in the case of magnetic also. But the magnetic equator with respect to the geographic equator, same the 17 degrees angle it makes as magnetic axis which makes with the geographic axis. Right? Now, here you should know or you should understand coming to the earth terrestrial magnetism, the most important terms. Before going to knowing these terms, you should have some idea regarding this about the Earth magnetic field. Earth magnetic field, how it is exists, how we call it as, which is South Pole, which is the North Pole. Do you have idea regarding this?
Um, no, sir.
Okay. Which we will take as a South Pole, which we will take as a North Pole.
So like the northern hemisphere is north and no,
Hmm.
like
Southern
the
hemisphere.
not hemisphere, but like yeah, the top part of the northern hemisphere will be like North Pole, and bottom part of the southern hemisphere will be South Pole.
I have a question to you.
Yes, sir.
When you are taking a bar magnet from the North Pole, magnetic field lines will go out, okay, and will enter into the South Pole. Means at the south pole, all the magnetic field lines enter inside. Okay. Now, if you take this is a magnetic axis, let us say this is a geographic north, this is a geographic south, then it is magnetic south, and this will become magnetic north. Okay. Now here, one understanding method. This is normally whenever we are hanging any magnet or a magnetic compass, right? The magnetic compass always shows geographic north-south direction, right? So whenever it is showing the geographic north-south direction, we understand that we understand that this is only geographic north, but this north pole of a magnet is attracted by whom? South pole of a magnet on the earth, right? This south pole of a magnet attracted by whom? North pole of a magnet of the earth. Okay, but it is twisting with some angle theta. This whatever the magnetic compass is there, that shows like little declination, means little tilting, it shows angle, but finally it shows this is a south, this is a north, right? But whatever magnetic north shows, whatever hand magnet or compass which is showing the direction, that is actually opposite direction of that magnet. Okay, but that is geographic north only, actually geographic north only. This is the confusion that people are having here. Here the thing is that usually, what we say, when you hang a magnet, it appears like this. Magnetic pole, magnetic field lines on the surface of the earth, always it is entered at the north pole, leaves at the south pole. But in the geographic, it enters at the south pole, it leaves, means it emanates the magnetic field lines at the north pole. At the north pole. Okay, so this is a little confusing in representation. The people, while they are representing, since this is magnetic north at the geographic south, we call it as this is a south seeking pole. What is that? South seeking pole. South seeking pole means south is attracting towards this side. So, are you there?
So, your video got stuck and I couldn't hear you.
Okay. Now, what I am trying to say here, whenever you are taking this, yeah, if you are taking this is geographic north, geographic south, whatever we are taking like a magnet here, straight. This is we are writing magnetic north, magnetic south. Okay, magnetic north, magnetic south, in the sense we call it is north seeking pole. This is south seeking pole, we call south seeking pole. North seeking pole, we call seeking pole, we say it is, because when you hang a magnet, it shows the proper direction. This shows it is actually geographic north. So we will write this is also magnetic north. We will write this is as magnetic south. But these all exactly not the north and south. Okay. Why? Here magnetic field lines are At the South Pole, it is leaving. At the North Pole, the magnetic field lines are entering. Otherwise, in common bar magnet, what happens? Magnetic lines is leaves at the North Pole and enters at the South Pole. And inside, south to north it travels. Okay, this is the way actual geographic magnetic field is existing, or terrestrial magnetism is existing. Okay, now further if you go, we need to know why the magnetic compass when you are hanging. Listen, when you are hanging a magnet or magnetic compass, it twirls. Twirls in the sense it shows little direction like this, not exactly horizontal. Why? We know that magnetic axis, which makes some angle with respect to geographic axis, right? Polar axis. Same way, magnet also when you are hanging, it shows with some angle, inclination and declination with respect to horizontal axis that we are going to discuss. If the magnetic axis is changing, then automatically the meridian also will change little amount. Means if you are holding bar magnet, for example, at the center of the earth, it shows the different direction. And if you go at the middle of the center of the earth and poles position like Canada, Northern Canada, uh, otherwise South America, that region, if you go, there it will be different. Okay, because that is comes towards a polar region. And other than these two positions, if you check, it shows the deflection different. So how we will get to know that magnetic meridian? What is this magnetic meridian and geographic meridian? As we studied that magnetic meridians and geographic meridians are the planes, vertical planes, which is along the axis of the geographic meridian as well as magnetic meridian. We studied already, like it appears like when you are looking at the books. These are the two books. The two books which are seeing, like these are the two planes. Now the appearance is like this. Okay, I'm holding like this now. Okay, one is a magnetic meridian, other one is a geographic meridian. Okay, now if you see between them angle theta, this is looking little up, this is looking little down. So the angle between the magnetic meridian and geographic meridian is called as declination at that place. What is that? Declination at that place. It changes place to place. It changes the declination place to place, obviously. Now, here you can see some lines shown on the map through a places that have the same declination are called isogenic line. For example, anywhere it will not shows the change in the declination that we call as isogenic line. Isogenic line. If the line drawn different places where declination is happen or taken place, that type of line is called as agonic line. Means if there is no declination between the magnetic meridian as well as geographic meridian, like this in the case of planes, then that is we call as agonic line. If everywhere if it comes same along the line, then that is isogonic line we call. Of course, this is extra general knowledge, that 2 points. Next, dip or inclination we call. What is the dip? What is the inclination? Dip or inclination means what? Both are same only. When your axis, when you are holding a magnetic compass, you will find the other side. It is looking down. Means Here the planes are down, there the axis is down with respect to the plane that you can see here. This is a resultant magnetic field beta. Resultant magnetic field which shows the direction. With respect to what? With respect to this horizontal component. So whatever the angle made by the resultant magnetic field with respect to horizontal component is called as dip or inclination we call. Dip or inclination, the angle between the horizontal component of the earth magnetic field and the resultant magnetic field of the earth is called as dip or inclination. It is 0 at the equator and 90 degrees at the poles. 0 at the equator, 90 degrees at the poles means you can understand here. 0 at the equator. When you are coming to the equator, since you are holding that it is at the equator, it's horizontal direction. You are keeping like this magnetic compass at the equator, right? What equator shows all the magnetic field direction with respect to horizontal, because equator position is completely horizontal direction, right? It quite perpendicular to the axis, polar axis. So there it is obviously 0. Okay. Now coming to the 90 degrees. When it will be 90 degrees? 90 degrees at the pole they said. Obviously, if you go to the poles, the angle of dip, how it will be changes. How much it will be changing? 0 in the sense what it will be 0? Look at here. The angle which you are seeing. Wait a minute. Yeah, I'll show you with the pen. This angle will be 0. What happened at that time? This B will act along the BH. So dip will become 0 at the at where? At the equator, because magnetic resultant magnetic field along the horizontal direction will act. Now coming to the when you are reaching to the poles, okay, poles in the sense obviously this is horizontal component. When you go to the poles of the angle of dip completely vertically turns. It makes 90 degrees. This delta become, this B comes along the vertical axis, then it will be 90 degrees. Right? So this is we call as dip or inclination. Dip or inclination we call it is. Now the next. Here also two important lines, isogonic and agonic lines same way. The lines drawn on a map, particular map which with respect to magnetic when you are measuring through a places that have the same dip. At every point if it is having the same dip are called as isoclinic lines. And at the same time if there is a zero dip, that is called as aclinic line. Zero dip, it happens along the equator line only it happens, right? So aclinic line we call it is. Here we learn declination is one term. Declination is the angle between the magnetic meridian and geographic meridian, between the two planes. Okay? Dip or inclination is nothing but the angle between the horizontal component of the earth and resultant magnetic field of the earth is called as dip or inclination. This dip is 0 along the equator. Okay, or whenever it is at the equator you are trying to measure, the dip is 0. But when you are measuring along the poles, means at the poles, sorry, not along, at the poles, when you are trying to measure, then automatically the magnet will turns into the 90 degrees angle. Means the dip will be makes the resultant magnetic field with the horizontal component is 90 degrees. Okay, this is two important terms. Apart from this, we are having the next most important term is horizontal component of Earth's magnetic field that we written as BH. You can see, I think, horizontal component of magnetic field you might have understood till now. Horizontal magnetic field, which we call the line which is there along the equator, the total intensity of the Earth's magnetic field. Okay, the total intensity of the Earth's magnetic field does not lie in any horizontal plane. Okay, instead of it lies along the direction at an angle of dip to the horizontal. So now we say the component of the Earth's magnetic field along the horizontal at an angle delta is called as horizontal component of the Earth's magnetic field. That we will write. We studied the vectors resolving components, right? The resolving
Yes.
component in the sense this is a BH, sorry, B. B is a magnetic field vector, nothing but here resultant magnetic field of the vector, which is making an angle theta with the horizontal axis, that is delta. We call it as dip in reverse direction. So now I can write this is B in the sense along the horizontal direction, this is BH equal to B cos delta I can write. This is B sine delta I can write. This is if you take in reverse direction, this is the resultant magnetic field which making an angle delta with the horizontal component. Now we are calling this is as a horizontal component of the Earth's magnetic field. When you are resolving D along the vertical axis, then vertical component dV equal to d sine delta and horizontal component dH equal to d cos delta. Now, the resultant of this vector, nothing but magnetic field. Always we know that resultant we will write under root of d horizontal magnetic field square plus vertical magnetic field square. If you take, you will get the total magnitude or resultant magnetic field you will get in the B. Now, from this we will find the direction of this magnetic field also. What is the direction of magnetic field? We know from earlier also we studied that is when you found a resultant of any vector, you can also find the direction of that vector. The direction always in terms of tangential form, that is tan theta equal to vertical component by horizontal component we will write. See, look at here, magnetic compass, how it is deflecting that they are showing the direction. This is a one horizontal component, this vertical component, and this is actually the resultant component. Okay. Now, with respect to the axis, whatever it is making angle theta, that we say it is as a dip. Okay. But here we took with the theta that we can write a vertical component by horizontal component b2 by b1. This is we call as tangent law. What it is we call tangent law. So we studied now tangent law as well as horizontal component of Earth's magnetic field. Now, in terrestrial magnetism, we study the components. Is first one is we call as magnetic declination. What do you mean by magnetic declination? Magnetic declination, it is the angle between the geographic meridian and magnetic meridian. Is called as magnetic declination. Now, angle of dip or magnetic inclination we call it as, that is a angle between the horizontal component of magnetic field of the earth as well as with respect to resultant magnetic field, whatever the angle is making, that we call as dip. Right? Now, next. Horizontal component also we have studied, that is BH equal to B cos theta or B cos delta we have taken, and the direction is determined with that tangent, that is tan theta equal to vertical component by horizontal component. This is these three all we call it as components of, or we say it is elements of terrestrial magnetism, and we studied about the terrestrial magnetism and its elements, magnetic elements we say.